Okay, so welcome to this, the first in the series of videos looking at solubility. So this is the last of the topics that we're going to be covering for this year, and we're just going to take you through this again page by page. But before we start, I just want you to have a little bit of a think about what we mean by solubility and what has to happen for an ionic salt to be soluble. So here I just have a simple glass of water. Okay, now it might not sound exciting, but when I put, so this is just table salt, so I've just got some sodium chloride here, and I've put that into my water, and if I give it a bit of a stir, you can see, or hopefully you can see if I hold it up a bit more, that all of it dissolves. Okay, so what I've got in here is just some salty water, and there's no, you can't see any more particles of salt there. So what's happened there is two processes have had to go on. Firstly, we need to break up the lattice. So we break the ionic lattice, and then we can hydrate the ions. In other words, we can surround the ions with water molecules. Now that might not sound all that interesting, but you have to remember that sodium chloride melts at 800 degrees Celsius. So that it turns the ions into mobile ions at that temperature. But I've just done exactly the same thing. I've got mobile ions. All the ions that were solid in here are now solution. So those ions are now mobile, and I've done that with just ordinary tap water at room temperature. Okay, so I can get the ions to be mobile in two ways. I can melt them, and in that case I'd need to take it to over 800 degrees Celsius, or I just need to get them wet, put them into some water. So it tells us something about the strength of the hydrogen bonding and the strength of the hydration enthalpies as well. Okay, so we said there are two processes, remember, that must occur. First of all, the lattice has to be broken up, and then the ions can be hydrated. In other words, they're surrounded by water molecules. Now, we studied a little bit of this when we looked at Born-Haber cycles. Okay, and we came across the lattice enthalpy. And just to remind ourselves, it's the enthalpy change when 1 mole of the solid is formed from its constituent gaseous ions. So because we're not having to overcome any bonds in order to make my lattice, and we're only making bonds, we're not doing any breaking of bonds, this will always be an exothermic reaction. So this is always going to be exothermic, okay, because bonds are being formed. In terms of entropy, on the other hand, we would always expect it to lose entropy. The reason for that is we're going from gaseous ions infinitely far apart, and we're forming a solid lattice, so there are less ways that the ions can therefore be arranged. So this will always be a loss of entropy. Okay, so we're just going to have a look at some of the equations for these. For magnesium oxide, for example, the equations are quite straightforward. You've just got your gaseous ions, in this case magnesium, gaseous ion, and an oxide ion coming together to form 1 mole of magnesium oxide solid. Nice and straightforward. Don't muddle it up with the enthalpy formation, which is slightly different. So if I do one more, calcium plus this time 2 lots of the chloride ions, because remember I'm making 1 mole of the ionic lattice, and I need 3 moles of ions to do that. Okay, but breaking up the lattice, remember, is only half the process. We've also, once we've got our lattice broken up, we need to hydrate our ions. Okay, so we've got two new definitions which you need to learn: hydration enthalpy and the enthalpy of solution. Okay, so hydration enthalpy is the enthalpy change. So it's the enthalpy change when 1 mole, and it's pretty much always 1 mole of something does something, 1 mole of an gaseous ion is completely hydrated by water. What this means in practice is that to form an infinitely dilute solution. And so, for example, if we have an example of this, we'd have some sort of iron with a charge on it. We're going to add water, and we're going to make 1 mole of our aqueous iron. Notice it's starting off as gaseous ions. The enthalpy of solution, this case, is the enthalpy change again. Enthalpy change when 1 mole of the ionic solid dissolves in water to form an infinitely dilute solution. Basically, that means if I added any more water, there wouldn't be any energy change on that whatsoever. So again, I can do a little example of this one. If I have my ionic lattice, it's going to be a solid this time, and I'm going to add water, and that's going to turn them into the aqueous ions, whatever those aqueous ions are. Okay, so a substance to dissolve, 2 processes have to occur. The energy has to be used to break up the lattice. Now remember, the enthalpy of lattice is an exothermic reaction, and we're doing the opposite. So it will have a value equal to the lattice enthalpy, but have the opposite sign. So that will always be endothermic. Then the energy is released on hydration of the resulting ions, and that will always be a negative value. So basically, enthalpy of solution is a balance between these 2 values. So our enthalpy of solution, we say it is the energy released by hydrating the ions, take away the energy required to break up the lattice. And this is what largely determines whether a salt is soluble or not. So the more exothermic this value is, the more likely it is to be soluble. Okay, so we started looking at lattice enthalpy and enthalpy of hydration. We're going to look at those in a little more detail. And we're going to look at the factors that affect these. So we're going to start looking at the lattice enthalpy. So we know the lattice enthalpy will be more exothermic. In other words, it will release more energy when the lattice is formed if the ionic charge is large and the radius is small. We're actually back to our 2 old favourites, size and charge, and they determine a lot of different things in chemistry. So we've got these 2 ionic substances which we're comparing, this one which has 2+ charges and this one which has 1+ charge. So we would expect this ionic substance to have the higher lattice enthalpy, in other words to release more energy when it's formed compared to this one. The reason for this is that we've got smaller ions and they're more highly charged ions, therefore the attraction will be stronger and they'll release more energy when they're formed. It'll have a more negative lattice enthalpy. When you're talking about exothermic values, remember it's always better to say more exothermic because when we talk about larger and smaller, it gets quite complicated. A larger exothermic value would be a bigger negative number. So we tend to say it becomes more or less exothermic. Okay, so we say the smaller the ions and the higher the charge, the stronger the lattice is going to be. So our delta H lattice for this one is going to be more negative, or we say more exothermic. Therefore, more energy is given out when the lattice is formed. We can actually quantify that using something called Coulomb's law. Don't worry about it too much. It's not something you need to learn, but it does give you an idea about what is going on. It's easier to see in my other notes. So this is quantified by what we call Coulomb's law. Don't worry about this too much. You don't need to know this. But you can see that the force, the electrostatic force, is dependent on the charges, Q1 and Q2, that's the charges of the different ions, and it's divided by r squared, so that's the distance between them. So you should be able to work out that as these two increase and this decreases, the force increases. This is not something you need to be aware of. Also remember that this lattice enthalpy values are theoretical values based on this calculation, which treats the charges as point charges. The actual values we get from the Born-Haber cycle. So on the last bit of this page, we're just going to compare the difference in lattice enthalpies. So the first one we're going to look at is lithium fluoride and sodium fluoride. Well, the lithium fluoride has a more exothermic lattice enthalpy because it's got a bigger negative number here, and that's because it's a smaller cation. Therefore, they can get closer together, stronger attraction, stronger lattice, more exothermic. Okay. Here, on the other hand, we've got rubidium and potassium. This time potassium is the smaller, so it can approach closer, again, stronger. These two cases, we've got two factors which are going on. The magnesium has both a higher charge and a smaller radius, so there's a much stronger attraction again compared to the sodium. Do notice it doesn't have any impact having the number of ions present. Because these are a lattice, this doesn't actually tell us the number of each species present, it just tells us the ratio in which they are present. So the fact that you've got two sodiums here and only one magnesium here does not have any impact on this value. Okay, so this is the last page we're going to be looking at in this video. This is page 5. And again, we're still talking about lattice energies. So here we're comparing rubidium fluoride with strontium fluoride. Well, strontium is in group 2, rubidium is in group 1. So the strontium is going to have a 2+ charge and the cation is going to be smaller. Therefore, it's going to have the more exothermic lattice enthalpy. Here, cesium and barium we're comparing. Well, barium again is a group 2 cation, so it's going to be smaller with a higher charge, therefore a more exothermic lattice enthalpy. Last but not least, we're going to be looking at copper 1 oxide and copper 2 oxide. Well, again, the copper 2 oxide is a smaller ion with a higher charge, therefore more exothermic. So again, we just need to consider size and charge. So looking down group 1, we would expect the lattice enthalpy to become less exothermic because the cation radius increases because you've got more shells of electrons, so the larger ions are pushed further apart and therefore attract less strongly. If you only consider lattice enthalpies, and it's important that we point out here we're only thinking about lattice enthalpies, the melting point would decrease on descending the group because the lattice would be less strong and less energy would be required to overcome it, and the solubility in water would increase on decreasing the group, again because you'd require less energy to break up the lattice. But as we've not considered the hydration, that's not the whole story. So we need to consider hydration along with lattice and put those two things together to work out the enthalpy of the solution. And that's what we'll do in the next video. Okay, so that finishes this little video looking at the start of the enthalpy of solution. And what we've basically been looking at today is the lattice enthalpy. In the next video, we're going to be looking at the hydration enthalpies, and then we're going to be combining the hydration and the lattice to make the enthalpy of solution. Remember that the more exothermic the enthalpy of solution, the more likely it is that the solid will dissolve. But note I said that it is more likely that the solid will dissolve. I don't say it definitely will dissolve, because there's one factor we haven't talked about yet. I'm going to talk about that later on, and that is entropy.